Welcome to New Findings of the Universe. Today, we are traveling 40 light-years away to one of the most famous exoplanet systems ever discovered. TRAPPIST-1, a tiny red dwarf star, cooler and smaller than the Sun. Surrounded by 7 Earth-sized planets packed so tightly that their orbits look almost unreal. For years, this system has been described as one of our best chances to study rocky worlds. And at the same time, one of the hardest systems to understand. And the reason is not the planets. The reason is the star. TRAPPIST-1 is not calm. It flares, it erupts, it changes, carries magnetic storms and star spots that constantly reshape the light we receive. And when astronomers try to study a planet's atmosphere, they are not truly looking at the planet itself. They are looking at starlight that has passed through the planet's atmosphere during a transit. That light is supposed to carry a chemical fingerprint. But if the star's own surface is covered in dark spots and bright active regions, then the fingerprint can become distorted. For years, this created the biggest mystery in the TRAPPIST-1 story. Were we actually seeing planetary atmospheres? Or were we seeing the star disguising itself as a planet? In some cases, the same kind of spectral distortion that comes from star spots can mimic gases like water vapor, methane, or carbon dioxide. And that means something terrifying for exoplanet science. We could detect a false atmosphere, or we could miss a real one. This is why the James Webb Space Telescope changed everything. Not because it took one stunning image, but because it allowed astronomers to measure something that had never been measured directly before. The spectral signature of magnetic surface features on an ultra-cool M8 dwarf star. That may sound technical, but it is the key. Because once you know what the star looks like when it is active, you can finally correct the planetary data with precision. And yes, the study that revealed this was published months ago. But its impact is not temporary. It is foundational. It is the kind of result that will shape every future TRAPPIST-1 observation from this point forward. Stay with me. Subscribe to New Findings of the Universe. Because this is one of those rare moments where a problem that blocked an entire field finally begins to crack open. To understand why this breakthrough matters, you have to picture what TRAPPIST-1 really is. It is an ultra-cool red dwarf, classified as an M8 star. That means it is far dimmer than the Sun, far cooler, and far smaller. In a simple mental picture, you might imagine a quiet red ember in space. But TRAPPIST-1 is not quiet. It is magnetically extreme. The planet's orbit closes in, so close that if TRAPPIST-1 were placed where our Sun is, 7 planets would fit well inside Mercury's orbit. This tight architecture is amazing for transit observations. The planets cross the star frequently, giving astronomers many opportunities to measure them. But it also means the planets live inside a storm. They are constantly exposed to flares and magnetic disturbances. This creates 2 major problems. The first is physical habitability. Strong flares can strip atmospheres. They can break molecules apart. They can turn a potentially Earth-like world into a dry, airless rock. The second problem is observational. Even if a planet has a beautiful, stable atmosphere, the star can make it nearly impossible to measure. Star spots are cooler regions. Faculae are hotter, bright regions. Both change the star's spectrum, and the spectrum is everything. If you do not know the exact spectral profile of those features, you cannot remove them properly from the transit data. For years, astronomers were forced to guess. They built models. They assumed spot temperatures. They assumed how much of the surface was covered. And they tried to subtract the star's influence from the planet's signal. But this is like trying to clean a window when you do not know whether the smudges are inside the glass or outside. You can wipe too much and erase the view, or wipe too little and leave the distortion behind. That uncertainty became TRAPPIST-1's biggest scientific obstacle. Not the distance, not the planets. The star itself. Its magnetic personality was contaminating everything. And this is where the story becomes almost poetic. The very thing that made TRAPPIST-1 difficult, its flares, became the key to solving it. Because with JWST, astronomers realized they could use flare events as natural experiments. Moments where the star's surface was rearranged in real time, allowing the hidden features to reveal themselves. The study focused on a sequence of major stellar flares. Normally, when a star flares during observation, astronomers groan, because flares flood the data with extra light and destroy the clean baseline needed for planetary measurements. But in this case, the researchers did something different. They treated the flares as a tool. Using JWST's nearest instrument, they performed time-resolved spectroscopy. This means they did not just collect a single spectrum. They collected spectrum continuously, tracking how the star's light changed before, during, and after each flare. And that is when something strange appeared. After each flare, the star did not simply return to its original state. In certain wavelengths, the star remained persistently brighter. At first, that might sound like a normal flare afterglow, but the timing and the spectral behavior did not match typical flare decay. It looked like something on the surface had changed. On the Sun, we know that intense flares can destabilize sunspots. Sunspots are regions of strong magnetic fields that suppress convection, making them cooler and darker. But a flare can reorganize magnetic structures. It can disrupt those regions, weaken them, and sometimes erase them. The data suggested something similar was happening on TRAPPIST-1. The flares were removing dark spots, and by comparing the spectrum before and after, astronomers could directly measure the spectral signature of the disappearing features. That is the breakthrough. This was not an indirect inference. It was not a model based on assumptions. It was a direct measurement of a surface feature on an ultra-cool M8 dwarf, the first of its kind. Even more importantly, the results showed that the star spots were only a few hundred Kelvin cooler than the surrounding photosphere. That detail matters because many previous models assumed much stronger temperature differences, and those assumptions could dramatically distort how planetary atmospheres were interpreted. In other words, TRAPPIST-1 had been hiding its planets behind a mask. And for the first time, JWST allowed astronomers to measure the mask itself. When people imagine exoplanet science, they often picture a telescope discovering life by simply looking at a planet. But real atmospheric detection is far more delicate. The signals are tiny. They are buried inside starlight. And the biggest danger is false detection. In a transit spectrum, the difference between a planet with an atmosphere and a planet without one can be extremely small. If the star's surface is changing, those changes can create features in the spectrum that look like gases. For TRAPPIST-1, this problem was so severe that it threatened the entire promise of the system. Before this new measurement, stellar contamination was one of the largest uncertainties in exoplanet research around active red dwarfs. And red dwarfs matter more than almost any other star type, because they are the most common stars in the galaxy. The key outcome of this work is that astronomers can now subtract TRAPPIST-1's magnetic surface signature with far greater precision. This means fewer false positives, fewer cases where water vapor appears in a spectrum only because the star was spotted, fewer cases where methane seems present but is actually an artifact of stellar variability. And it also means fewer false negatives. Real atmospheric signals may have been hidden by stellar noise. Now, with better correction, those signals have a better chance of being revealed. This is especially important for the planets in the habitable zone. TRAPPIST-1 has worlds that receive energy levels comparable to Earth. These are the planets that drive the fascination. But they are also the planets most vulnerable to stellar activity. This study also advances stellar physics. It suggests that even ultra-cool dwarfs share processes with the Sun, where powerful flares can erase magnetic surface features. That hints at common plasma behavior across very different stars. And understanding that behavior is essential. Because stellar magnetism shapes planetary climates, atmospheric stability, and radiation environments. In other words, this is not just about TRAPPIST-1. It is about building a reliable method for studying rocky worlds around active stars everywhere. One of the most exciting ideas that emerges from this work is a shift in strategy. For a long time, stellar activity was treated as the enemy. If a star was too active, astronomers considered it a poor target for atmospheric studies. But now, something surprising becomes possible. Activity can become an advantage. If flares can disrupt and erase star spots, then observing a star during flares can reveal the properties of those spots. It is like the star is briefly rearranging its surface in a way that exposes what was hidden. That means flare timing could become a deliberate observational technique. Instead of waiting for quiet periods, astronomers might plan observations specifically to capture flare events. Not because flares make the data cleaner, but because they make the surface features measurable. With enough events, you can build a better map of how the star behaves. And once you have that, you can correct planetary spectra more accurately. This is the part that matters most for the search for biosignatures, because biosignatures will be subtle. They will not appear as a single, obvious molecule. They will appear as combinations, patterns, and ratios. If the star can mimic those patterns, then the field risks one of the most dangerous mistakes possible: announcing a biosignature that was actually stellar contamination, or failing to recognize a real biosignature because the star erased it. This method is also widely applicable. Many nearby targets are active red dwarfs: Proxima Centauri, LHS 1140, and dozens of others that will become major JWST targets. The same approach works. It could reshape how exoplanet atmosphere studies are done across the entire field. At the same time, this does not erase the habitability problem. Even if we can measure atmospheres better, strong flares still threaten atmospheric survival. A planet can be in the habitable zone and still be uninhabitable because its atmosphere is constantly being eroded. But this is where the breakthrough truly shines. It does not promise life. It promises clarity. It allows astronomers to separate what belongs to the planet from what belongs to the star. JWST is revolutionary, but it is not the final instrument in this story. It is the beginning of a new era. And TRAPPIST-1 is becoming one of the most important training grounds for that era. One major frontier is ultraviolet radiation. JWST excels in the infrared, which is ideal for detecting many atmospheric molecules. But the most destructive part of stellar activity often occurs in ultraviolet. Ultraviolet radiation can break molecules apart, heat the upper atmosphere, and drive atmospheric escape. To fully understand whether TRAPPIST-1 planets can hold atmospheres, we need to know their ultraviolet environment. That means combining JWST data with other observatories: space telescopes that can observe ultraviolet, ground-based telescopes that can track activity over long periods, and next-generation instruments that can build more detailed models of stellar surfaces. The Extremely Large Telescope, for example, will provide unprecedented resolution and sensitivity from Earth. While it cannot replace JWST, it can complement it by tracking spot evolution and magnetic behavior in ways JWST cannot. This study also helps the field mature. Exoplanet science is moving from discovery to characterization. In the early years, finding a planet was the goal. Now, the goal is understanding what that planet is made of, whether it has an atmosphere, and whether it could support life. That shift demands higher standards. It demands that astronomers understand the star as deeply as the planet, because the star is the light source. And if the light source is unstable, every measurement becomes uncertain. What we are seeing is the field building a stronger foundation. Less hype, more reliability, fewer spectacular claims, more careful conclusions. And that is exactly what is needed if we ever want to make a true life detection claim that holds up for decades. TRAPPIST-1 is teaching us that the hardest targets may produce the most valuable lessons. Because if we can solve the contamination problem here, we can solve it almost anywhere. When people say JWST solved TRAPPIST-1's biggest mystery, they are not talking about a dramatic discovery like alien life or a hidden signal. They are talking about something more important for science. They are talking about trust. The biggest obstacle in TRAPPIST-1 research was that astronomers could not fully trust atmospheric measurements. The star was too active. Its spots and magnetic features distorted the spectrum. And without knowing the true spectral profile of those features, every atmospheric claim carried a shadow of doubt. This study removed a major part of that doubt by using flare events and time-resolved spectroscopy. Astronomers directly measured the signature of the star's surface features. They no longer have to guess. They have an anchor point. That anchor changes everything. It means future transit spectra of TRAPPIST-1 planets can be corrected with far greater accuracy. It means reduced uncertainty. It means fewer false detections. And it means that the planets in the habitable zone can finally be studied with a level of precision that was not possible before. This is why the study remains relevant even months after publication. It is not a single headline. It is a calibration. It becomes part of the baseline for all future work. And it also affects how we think about red dwarfs in general. Since red dwarfs dominate the galaxy, understanding their magnetism is not optional. It is essential. The first potentially habitable planets we confirm in detail may very well orbit stars like TRAPPIST-1. This work also reminds us that astronomy is often about removing obstacles rather than finding instant answers. Before you can find life, you have to remove the noise. Before you can interpret a spectrum, you have to understand the star that created it. TRAPPIST-1 is no longer a system where everything is suspicious. It is still challenging. It is still active. But now it is interpretable. TRAPPIST-1 has always been a paradox. It gave us 7 Earth-sized planets, including several in the habitable zone, but it wrapped them in a storm of magnetic activity. It was like the universe offered us a treasure and then placed it behind fog. This JWST breakthrough did not remove the fog completely, but it gave us a way to measure the fog itself. And that is the turning point. Because once you can measure the contamination, you can correct for it. The first direct spectral measurement of magnetic surface features on an ultracool M8 dwarf is not just a technical milestone. It is a door opening. It signals that exoplanet science is entering a phase where precision is catching up with ambition. It also changes the narrative around stellar activity. Instead of seeing flares only as destructive noise, astronomers can begin to see them as opportunities. Moments when the star reshapes itself in a way that reveals hidden information. Moments that can be used to map surface features and refine atmospheric corrections. And that is the kind of mindset that drives real discovery. Not waiting for perfect conditions, but learning how to extract truth from imperfect ones. The search for life will not be won by a single telescope or a single study. It will be won by building methods that can survive scrutiny, by reducing false positives, by understanding stars as deeply as planets. TRAPPIST-1 will remain one of the most important systems in the sky, not because it is easy, but because it forces us to become better. And as we become better, the universe becomes clearer. If you enjoyed this episode, subscribe to New Findings of the Universe. Share it with someone who loves astronomy. And stay here because the next chapters of exoplanet discovery are going to be even more surprising than the last.